Good afternoon, everyone. Morning? Okay. I need coffee for sure. I had a bad night today. I was working on something that you'll probably see in the end of the talk. Good morning, everyone. My name is Vitaly Kamluk, and I'm here with my friend Nicolas Collery. I'm myself from Kaspersky Lab. Nicolas is from DBS Bank. So today we're going to talk about full disk encryption from perspective of forensic analyst, malware analyst that needs to do work remotely. Imagine that you have a problem somewhere distant from your office and you need to locate and copy malware or understand how the system was breached. But you have a challenge of full drive encryption that uses proprietary algorithm that has no support from the open source world. And a little warning, if there are some underage individuals in the room, it's time to leave. Also, if you are scared of deep technical content, I recommend to leave now, because we have pretty compressed technical presentation. There will be very little water. So, do you want to say a few words about yourself? Okay, we'll skip and go straight to the point. We actually presented last year about this project. It's an open source project called BitScout that allows you to build your own live CD that you can use for remote digital forensics and malware analysis and triage. So it's minimal in size, and it has certain principles that we implemented there. It has to be forensically sound live OS. That means it has not modified the system where it's booted. It should be simple and customizable. It has to be extendable at runtime, so you have to install it. You should be able to install additional packages and libraries and so on. It shall work over slow and unstable networks. We actually use it many times, including some cases where a computer in Africa was compromised and I had to exfiltrate, some evidence of the compromise and analyze that without copying the whole disk. It's using your VPN certificate and SSH keys to provide you remote access to the box. So basically, it's a live CD that runs Linux, starts OpenVPN, provides you with SSH access over this VPN, so that you can use a bunch of open source tools that is available in the Linux world to analyze the disk, to analyze the malware, analyze its configuration files, and copy any files that you want from that system. And in this talk we delivered last year, there was assumption that there is no full disk encryption. The difference of this year is that we are dealing with full drive encryption now. So it's minimal in interface. BitScout has the only graphical picture on the boot splash after you boot it. It has to keep the size low. That's why the user, the owner of the machine, compromised machine, sees only the screen with a very simple text-based UI where the owner can enable certain features, maybe set up network if required, and provide access, approve access of the for the export remotely connecting to that host to specific drives. The idea of this system also is partly based on layers of virtualization to protect from accidental tampering or malicious export working remotely and then planting some evidence. So the export actually works within containers, so we use Linux containers for this. So the export SSH into the container, which has certain layer of isolation, and it's running as an unprivileged user. However, there is a root user simulated within the container, so that allows you to install additional packages or change pretty much any file inside. So the only thing that the owner needs to do, normally if it's DHCP, everything is automatically configured. The only thing that the owner needs to do essential is to map physical drive to a virtual drive within the container that is available as a read-only block device to the expert. That's how it's done. Like I said, there are multiple layers of virtualization that protect from accidental changes of the source drive. Because if we are going to use this approach in court, for example, if you want to really acquire disk image in a forensically sound manner, we have to guarantee that there will be no changes done to the drive. So it has to remain untouched. That's why we have this live CD and everything is happening in the RAM. After you shut down machine, like not a single bit shall be flipped or changed on the hard drive of that machine. So this is essential. Now, network setup allows us to connect over VPN by default, but the user, of course, can enable direct access from the LAN. So for the demo, we will use direct access because it's just simpler instead of using VPN. So we can SSH directly into the box and control it. So certain ports can be forwarded from that container to the over the VPN to the expert, so that we can start additional services, including virtual machine, like we will show you in a few moments. Yeah, that's what I was saying about access from LAN, and also if you are the owner and the expert at the same time, if you use it in your own environment, in your own network, you can also log in to the host system, not to the container. Now let's, we have prepared 3 demos. We normally show it live, but due to the time constraints, it has to be faster than usual, and there is no space for typos and redoing things. So we're going to show some recording, and in the end, if we have time, I'll show you something that we prepared especially for Hack in the Box. So let's start from the first demo. You want to explain the?
Sure. So we have a compromised system running Windows 10. This system has a full disk encryption, as we explained, and is going to have some challenges to run all the tools that we commonly have. And as you can remember, we are over the network in a far away place where the expert is going to remote in. So the owner has created a live CD, has booted up the compromised system, and now will grant the permission that Vitaly just explained. So this is the booting of BitScout, a bit faster. Then the owner maps the network, grant the access to the expert, and will map the disk from the physical disk to the virtual disk in the container. So the owner will select specifically the disk he wants to authorize, SDA in that particular case, and will map it to evidence 0 in the container. All right, so now the expert can remotely connect to the virtual machine, to the container, and we will perform the analysis. So after a bit of setup, we can see the disk. So the disk mounted as evidence 0 will contain 2 main partitions. The first one is a small one, is the boot one, followed by the main disk that is 12 over gigs. And it is this disk that we will analyze. So we will look specifically at the offset. So we want to see what is the content of the disk. If we look at the content of the disk at the offset of the first partition, the boot partition, as expected, we are going to see it clear because it is where Windows is starting from. All right, so we can see the NTFS header. No surprise here. Now, let's calculate the offset for the second partition. And this time, when we see the content, well, it's encrypted. We can't recognize it. All right, so first, to prepare the demo, we are going to create a shared folder, and we are going to put some tools in it. So the expert from his machine will use SCP, copy the binaries we are going to use for the next demo. Then subsequently, so we have Process Explorer in particular. And then subsequently, we are going to create a virtual machine. The virtual machine will read the information from the mounted disk, and all the write instruction will be on a differential disk that will be stored in the QCO file.
Just to add a few words, the virtual machine will use the original hard drive in write protection mode. So all write operations will be sent to this file evidence to QCO. So it's like a differential file. And we're going to start now the original machine within the VM.
In any case, it wouldn't have been possible to do otherwise because Windows need to write certain things during the boot sequence. And as you know, the owner has mounted the disk as read-only. So once we have created that virtual disk, we are going to use it by creating a virtual machine. We are using QEMU. So here we can see that the virtual disk is very small. Windows has not booted yet. So we create the virtual machine now, and we are using this virtual disk as the main disk. We are also allowing to connect to the screen through a SPICE protocol. And lastly, we are allowing Samba to start to act as our shared folder, so we can transfer files between the virtual machine and the container. So let's connect to the virtual machine booting up of a SPICE. As explained, the disk is encrypted. We don't know what's the protocol, but then the owner will have to key the password. And the user that we can connect with is unprivileged. So let's verify that. We also know that this machine was known to have connections to a known command and control server. It has been identified by the SOC. So we just validate that. By doing netstat, we can see there is a connection to 131.255 and so on. So let's copy the tools from the container to the Windows. We cd to that folder, and then we are going to start Process Explorer. With Process Explorer, we can see that there's a PowerShell process running. We can see the connection made by the PowerShell, but we cannot have any detail because we are unprivileged, and apparently this process has been started with a higher instance. So we have access denied for the user or the process. All right, so we are unprivileged, and we want to use our tools as privileged user. So we are going to demonstrate one of the techniques. We stop the virtual machine, we dump the content of the RAM on disk, and then we are going to use the interactive console of volatility to examine and modify this memory file. So first, we know that on Windows, the first process started is called system, and it has a fixed process ID, process ID 4, and it has the highest authority on the system. So we will try to steal the security token of that process and affect it to our cmd.exe. So highlighted, we can see the security token of the system process. We can see the offset of the security token of cmd.exe. So now directly in the memory, at the offset of cmd.exe, we will allocate the security token of system. So the effect of that is that by right, if it works well, our cmd.exe now should be owned by system, allowing us to have full privilege on Windows. So as you can see now, we are in system, and we can start Process Explorer that was started from cmd as anti-authority system. So now we can see, it was a bit fast, but we can see the command line arguments of PowerShell, and for easier decoding of the payload, we will store it into Notepad, into a file, and we will copy that file via shared folder onto the container where the expert can manipulate it with all the Linux tools we are familiar with. So this is done. Now from the container, we can see our file, and then we can use base64 to decode the payload after removing the unnecessary stuff. So we can see doing so that we have the IP address highlighted 131.255, and it was the command and control server that the PowerShell was connecting to. And we also can see a security token that was used for the communication to avoid snooping by analyst. So that was the first demo. We managed to access the compromised machine. We managed to perform the forensics analysis on the live system. When I mean live, it has been booted up, but because of the mechanism we have explained earlier, there's no trace on the machine itself. Once we reboot, everything is gone. The second demo, we assume that there's no user to log into the machine. So we will have to first find a mechanism to log in and a second mechanism to elevate our privilege. The two techniques that we are demonstrating here are commonly used in penetration testing. We didn't invent it specifically. So for this, similar to the first demo, but using another technique, we are using the concept of virtual machine where we can save a snapshot. So we save the snapshot on disk using the save VM command from a QEMU. We can see the file that is 500 over meg, no surprise here. And then directly with xedit, we are going to modify that RAM disk, that RAM file. So we search for a specific string that we have identified that will contain basically a registry key where the accessibility system is working. And we are going to replace sethc.exe by cmd.exe. That will be convenient for us.
Just a quick comment. The sethc is the Windows standard executable that is started whenever you press Shift 5 times. By default, Windows starts in any context of any process, wherever you have been logged on or at logged in session. That one is designed to enable high contrast theme for people with lower eyesight, like bad eyesight. So, and this is the registry hive in the RAM of Windows OS that we have just modified to cmd.exe. You see, they change from sethc.exe. We're going to start cmd.exe by pressing Shift 5 times.
So we have directly modified the snapshot of the virtual machine. And now we just need to restore the snapshot. And by restoring the snapshot, when Windows will resume the execution, we indeed should have placed our trick. So we are pressing 5 times the Shift key, and then a console comes in. For convenience, we are just going to change the password of a privileged user, but we could have added our own or many other tricks to log in. So now that we have changed the password by typing 123 as a privileged user, we can log in as administrator. All right. So now we want to have access to the file system and do more analysis, because you will see after copying some of the tools, we identified as a malicious file, and we can't do anything from Windows itself. It's actually a rootkit, and the rootkit is preventing us from doing the analysis directly. So after copying our files, we go to the folder, and we will start Yara. Yara is a tool that will search for specific patterns on the disk, on any of the file. And we are looking for some generic malware signatures. And we see that there are 2 files that cannot be opened. We can see ntfs.sys that we will not analyze, and we can see something suspicious, at least from the name, perkiller.sys. So if we go now with the Explorer to the driver folder under System32.
So we're going to show you some side effects of rootkit activity on your systems.
So we can see the perkiller.sys file. So the file itself is not hidden. However, by looking at the properties of the file, we don't have access to any of the security information or any other meaningful detail about it. Then we decided to copy the file somewhere else. So first, we have some error by looking at the properties. When we copy it, let's say on the desktop, then we have yet another error. We can see the file cannot be copied.
It actually says that the CD is not inserted into the drive C.
So if we create a file, here a folder called perkiller, there's no problem. However, if we rename that file perkiller.sys, the system will not allow us to do so. Similar error. So maybe we should be tempted to open the file with Notepad or any other tool. So by starting Notepad on that specific file, we should see the content rightfully.
Notepad is my favorite anti-rootkit tool. You can detect the presence by just opening the file, and all kind of awkward messages will appear.
And if we try to open it directly from the UI, we will have the same kind of error.
It's a bit different in here. I just take a look because it says that the drive C probably is not formatted.
All right, so we need to find a way to access it. So one of the techniques that we found, again, it is not, the purpose of this presentation is not specifically to show all the techniques to do forensics, but leverage the capability of BitScard to boot virtual machine and have a lot of access.
So this is more applicable for triage, actually, when you can actively interact with the system and you see the traffic, you see the processes, you can dump them, you can inspect them in the lab. And you can even install security products if you want, like a scanner, and then go through the whole drive.
So here, I just started a process called Network Block Device Server. It will basically map the content of the disk and expose it as a service so that from the container we can connect to it. This requires elevation of privilege. So as a supervised mode, the owner has to allow this specific command. Once the command is exposed, we can see the server itself is responding and serving the content of the disk that is required. And therefore, we know we can have access to the disk. So now we just need to so the file is actually on the disk.
Just a few words. Actually, this network block device, you can export it right from the VM over the network, over the internet, somewhere in a different place. So you'll see the block device, which is of size equal to the drive on that infected system. And you can access any sector, any byte over TCP/IP without copying the whole image.
So since we have this network block device file that can be exposed, we will try to mount it and expose it to the system. First, we can use FLS from SlowSkit to look specifically for the offset of all the files and the metadata associated. So we can see some reading. We can see the content of the file system, and we can identify our file in the so we can identify our file. All right, so Percula is here. We can see it. Now let's mount the disk using the mount command, and we will create a MNT C drive. Once it is mounted, we just can access the remote file system as if it was local, and we can see the content of the file, and we can see, oops, sorry. Yeah, we could see the content of the file, and it was executable, and now we can copy and do the analysis of the rootkit.
So just to summarize what happened in the previous demo, we started the VM on the original system with write protection. Then we started the NBD service inside of that VM, and then we kind of exported already the decrypted block device, the drive C, that we can access over the network. We can mount it to our own system, and then export any files that we want or access any files that we want. Now, we will level it up a little bit. So imagine that we have a nasty malware that actually killed the system. So Windows doesn't even start in safe mode, in normal mode. And what can we do? Can we still extract files if we cannot leverage Windows itself? We cannot start NBD service anymore. So there is no Windows process started. It just goes into the blue screen whenever we try to boot it. Just a quick example of that. So it can be due to incompatibility with Windows version or just buggy rootkit. So what can we do with such system? So we're gonna copy some Python tools, minor tools that we created for this particular scenario, and we'll show you some additional techniques. So first we'll create files, pipes, that we will attach to the virtual machine's COM port, serial port. We're going to use that to communicate with some of the code inside of the VM. So we're going to actually patch the brain of the VM using the debugger attached to the hypervisor. So first we created these pipes. This is for input and output from the serial port. Then we're going to start QEMU, and you can see it's attached to the same diff file. This will start the debugger and the machine in suspended mode. Then we see that we specify the COM1 shall be attached to the guest.serial pair of files. It automatically appends .in.out. So once we run it, machine is suspended now. So next, let's see what we see at the screen. Oh, sure, there's a black screen. Okay, we'll skip that. Next, we attach the debugger to that machine. So GDB now is attached to the guest within the VM. So what we will do next, we'll set a breakpoint at this magic position, which is where BIOS of PC loads the MBR code. This is like will be the first byte ever executed when you start the PC, taken from the disk. So first, we press continue in the debugger, and this is where the first breakpoint it hits, and this is where full disk encryption loads its support for decrypt and filter drive to let Windows boot. It sets up certain hooks for the interrupts, for the disk I/O interrupts, to enable transparent access to the drive, and that code works in the real mode. So after that, the full disk encryption shall actually recover the original Microsoft Windows MBR and start executing that with the hooks for the disk I/O setup. So we're going to continue again to see when it hits second time. So now the full disk encryption software asks us for the password, and once we enter this, we hit our breakpoint. So now if you look at the location of this 7C00 in the RAM, there will be original Microsoft MBR code. So at this stage, this transparent access to the encrypted sectors is set up, and we're going to leverage this. So we will put our own code instead of the Microsoft MBR. It will be like a tiny implant that actually listens for the serial port, for the COM port, and it can help us read the sectors. So how do we actually put this into the RAM of the guest? For this, we'll leverage Linux feature to expose memory maps of the processes. So you can see there is a file that is inside of for every process. There is a file in the root file system where the memory maps are exposed. This is the beginning and the end of the map corresponding to certain module loaded into the process of QEMU. So our task is to find the largest memory region that shall, by size, be equal to the size of our guest RAM. So we're going to do a little bit of shell scripting, sort, and find the largest region of allocated memory inside of QEMU process to patch its memory live. Let's see. So we're going to add sort by the first column, which represents the size of the region. So you can see here 536 millions of bytes. It's actually 512 megabytes, which is equal to our RAM. So now we'll use this simple Python script that opens another file inside of the process, inside of the subsystem. And the file called mem contains physical memory, actually virtual memory of the process corresponding to QEMU. This is how we can access any region inside and patch memory of QEMU live. By this, we will patch the memory of the guest as well. So we use this script to insert this tiny snippet of code in 16-bit assembler that will do the job for us, the rest of the job. So look at these first bytes. So once we run it, you can see that MBR has changed. So and now it will be executed. And there is an infinite loop where it listens for commands on the COM port and does discrete operations. So next we are continuing the guest. So you see that actually it gets stuck in the infinite loop, and then I wanted to show you the partition before decrypting and after decryption. So we'll list the partition table. Oh, that's already okay. That's reading the sector from the drive through another tool that interacts with this implant inside of MBR. So probably you'll see the decrypted code here. So we pass the bit of QEMU that it will patch memory for a serial pipe file, and the offset to the disk sector that you want to read. So if you convert it to the hex and an ASCII, you can see that drive C now is decrypted. So we can access a sector. This is good, but how about accessing the whole disk? So for that, we wrote a fuse driver in Python that actually does sector by sector interaction and reads sectors on demand. Fuse actually, it's a nice technology that allows you to implement user mode drivers. So for this, we'll create a directory where we will map, we will create a virtual file that is an image, a projection of the whole decrypted drive C. And then we start this Python script. In the other terminal, I'll show you the contents of that directory. So it contains a file called disk. You see it's 12 gigabytes. Our RAM of the whole thing of the live CD is actually 4 gigabytes. Of course, it cannot contain the whole file. It's a virtual file. Whenever we access any part of this file, it will dynamically provide you with the data that you want. That's what Fuse allows you to do. And you don't need super privileges for that. So we open this disk and we can work with this. We'll navigate to the beginning of the drive C. You can see that it's decrypted partition. So now we can apply any other tools to work with the partition by passing the layer of full disk encryption. So some forensic tools just to list the partitions again. We're going to use that to list the file system contents. Of course, we can find interesting files. And you can see actually it prints plus every time you try to read a block of sectors from that VM. You see that it's reading and reading and reading because it's traversing the whole directory structure of that guest. You can see the files on that system, and you can, of course, inspect any timestamps, whatever you want for forensic analysis. This is cool, but how about accessing the files themselves and see them as a directory mounted to your system? It's possible as well. It requires a couple of supervised commands that should run outside of the container. So we're going to start the same Fuse driver with a few options to create another Fuse directory and then mount it. So here, essential is that we mount the NTFS partition to our live CD in RAM. Once we mounted this, we can go and just explore the folders and files through this VM bridge. And this is done before Windows started booting. That means there are no changes whatsoever. It is a clean image, forensically sound that you can copy off the network if you want, or on the USB drive attached to the same system. So far, it's untouched. It doesn't include any changes implemented, done during the booting. And of course, you can scan the files, you can access any file because there is no rootkit running. And yeah, this is the rootkit file. I think we ran out of time. Okay.
So we wanted to show you something. You can look for us outside maybe if you're interested.
So, yeah, basically what I was working on this night, I wanted to show I was asked whether it's possible by people who saw this previously, if it's possible to actually cure such system, if you can remove the files from it, if you can write to the encrypted drive. And apparently, theoretically it is possible, but practically it's not easy to do. So it requires some extra code in that implant that we put into MBR. But that's what I worked on this night. I think due to the time constraints, I'm not going to show you because it may take another 7-8 minutes. but it is possible to actually provide this write access, and then you can mount the file system in read-write mode, and then you can clean the system if you want. So in case you are stuck with proprietary encryption, which doesn't provide you any other external tools to mount this, especially from the Linux world, there are a lot of limitations, like for proprietary commercial products, then this approach allows you to inspect system and check it. And you see this is vendor agnostic, so we didn't actually modify and reverse engineer the code of encryption. We don't know how it actually encrypts. We just leverage the code, whatever is there, and we can do our job. That's it. Thank you very much.